Okay, we're going to continue on with chapter 14, which was on that recorded lecture that was posted the other day when we had our exam. So in that first part of that lecture, what we talked about was really phases and phase changes, and really sort of the energy that's associated with. You could use the you really use either one, but kilojoules is good. Other questions on that? Although the joule one is a pretty good one because like when you do specific heat with it, that's going to end up being in joules. So that's also probably a good one as well to sort of know. Other questions on that? Okay. So speaking of that, what we talked about was this idea of as we go from, say, solid to liquid or liquid back to solid, there's a certain amount of energy required just to do that transition of state, not changing the temperature as that occurs at the normal melting point or freezing point of a substance. For water, that's 0 degrees Celsius. And that is what's known as the delta H of fusion, or the heat of fusion. And that is that energy that's required really just to change, say, ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. For water, it is something like 6.02 kilojoules per mole, which roughly equates to about 335 joules per gram. And remember that the amount of energy required to do that change, it's the same regardless of sort of which way you're going. The only difference is sort of is it endothermic or exothermic. So as we go from solid to liquid, that's an endothermic process. And that means that the delta H here of fusion would be a positive number. Going opposite, we do have to remove the energy from liquid to bring it back into the solid state. So the delta H of fusion would be negative, heading in the opposite direction. Again, the number would be the same. Also, as we go from liquid to gas and gas back to liquid, bless you, that also occurs at the normal boiling point of a substance. And again, for water, that is 100 degrees Celsius where that occurs. There's also a certain amount of energy required to do that, which is the delta H of vaporization. And again, at the normal boiling point is where that occurs. For water, that is roughly 40.7 kilojoules per mole, and roughly 2260 joules per gram is the amount of energy required to do that. Once again, it would be a positive value going from liquid to gas and a negative value going from gas to liquid. We also saw there that obviously it takes a lot more energy to do that transition as you go from liquid to gas, and even vice versa there, because as you go from liquid to gas, you are completely breaking everybody apart from each other so that they could go into the gas phase and fly around. And also as they come back out of the gas phase, they're flying around. So it takes a lot of energy to slow them back down. So they kind of stick and go into the liquid phase than it does to just go from solid to liquid where they're relatively close to each other, as we can see sort of the difference of those values. We also saw a heating and cooling curve. Looks something like this. This is like liquid water, obviously gas, ice, which would be solid. And again, if that's 0 degrees Celsius, like 100 degrees Celsius there for water. Again, at these parts right here, this would be our delta H of vaporization. This part right here would be our delta H of fusion. When we actually change the temperature but keep the phase the same, which on these cooling curves and heating curves are pretty much when the line's kind of going upwards, that means that those guys are in the same phase all the way through, say those blue lines, but the temperature does change. If we want to associate basically how much energy is required to do that, that is our specific heat equation. Q is equal to ms delta T. Remember here, the S, which is our specific heat capacity, is really important. If it is not liquid water, you do not want to use 4.184, which is the specific heat capacity for liquid water, or that 1 calorie per gram per degree Celsius. We did an example there where we did go from ice, say, to steam, and when we get into those parts, you do have to use a specific heat capacity for, say, ice or thank you, gas in that particular case, which is about 2, for example, instead of 4.184. So remember, for liquid water, you are supposed to know the specific heat capacity, which is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. And that is the conversion between those two things. 4.184 joules in a calorie is our conversion factor. Now, if we do take something like we did in that example on the video, from ice all the way up to steam, we basically can figure out the energy associated with each of those steps along the way. And if we wanted the total amount of energy, as energy is a state function, we basically just need to add up all the individual steps. And that will give us our total energy basically to do that. Once again, like in that example, we went from ice to steam, which is all an endothermic process. So each of these guys will hit positive numbers when you calculate the energy. And when you add them all together, if we were to start again at the top there, like steam, and kind of bring it back down to ice, again, the only difference here is we're going to have exothermic. So everything will be negative. And that's why it's really important, as we talked about previously, so always make sure that you do final minus initial, especially when you're using a specific heat equation, as that is what is going to give you either a positive or a negative value. Any questions on any of those things there? Okay. So the rest of this chapter, we're going to talk a little bit about forces that hold molecules together. So the first type of force is actually one that holds an individual molecule together, and that's an intramolecular force. And an intramolecular force is within the molecule. So an example that we might have seen before, if we take something like an individual water molecule, the bonds that hold that together are covalent bonds between the oxygen and the hydrogen. And that is covalent bonding, and that's the intramolecular force within that. Also, if we have some type of ionic compound, they're held together by electrostatic attraction, and that also is an intramolecular force. They are the forces that hold individual sort of molecules together, and they are really kind of the strongest interactions that you could have. And they're definitely much, much stronger than, as we'll talk about here, intermolecular forces, which are those molecules that are the forces that hold molecule to molecule together. So intra, within the molecule, and that is different than intermolecular forces. Intermolecular forces, as I mentioned, are the forces that hold one molecule together with another. So again, if you had a couple of water molecules, that is the force that holds basically this one water molecule together with another. All intermolecular forces, which is a majority of what we will talk about here in this chapter, all the different types of intermolecular forces that we kind of touched upon as well in some other chapters, they all have really the basic interaction that's happening. And the basic interaction that's happening is basically positive and negative. So electrostatic attraction. So basically the positive side of one molecule is attracted to the negative side of another. And that's essentially how all intermolecular forces basically work. Some work stronger than others. Some need something to occur to allow it to have that sort of separation of charge, but they all basically is a very simple positive, negative side. So for example, here with water, oxygen is more negative, hydrogen is more positive. So that is the attractive force between those two. And that's known as hydrogen bonding, as we'll talk about, which is an intermolecular force. Once again, the intermolecular force here is always weaker than our intramolecular force that we talked about a second ago. And we know that again for that very simple explanation that we've probably talked about previously. When we go to heat something like water, we definitely break this bond here between the different water molecules, which allow them to separate. We know that because when we heat water, we don't get hydrogen gas or oxygen gas, which is what would happen if these guys were weaker. So we don't get those bonds to break. What breaks first is that weaker intermolecular force between different water molecules, for example, here, that allow them to go off maybe into the gas phase and stuff like that. So any intermolecular force that you find will always be much weaker than intramolecular forces, which basically consist of, in most cases, electrostatic attraction like you have in ionic compounds and covalent bonding that you have in molecular compounds. The strength of these intermolecular forces play a really important role in terms of how molecules interact with other molecules, and some of that stuff that we talked about in previous chapters, that idea of like dissolves like. When we have things that basically will interact with other molecules the same way that they can interact with themselves, they basically can use the same type of intermolecular force. They will be very soluble in one another, and that's why we have ionic things and polar things are very soluble in each other, because positive negative attraction works really well. We have polar and polar things. They both have a positive side and negative side. And that's also why nonpolar and nonpolar things work well with each other, because they both are using the same type of intermolecular force that they use with themselves as they would use with somebody else. That's also why when we cross over from polar to nonpolar, we run into trouble, because one wants to use a specific type of intermolecular force, the other one is using a completely different one, and they really don't match up for the long period of time, and they have no way to maintain that over the long period of time as well. It also affects things like boiling points and melting points and freezing points. So things with a really strong intermolecular force typically will have a high boiling point because they're held together by a really strong force. It takes a lot more energy to break them apart into each other, into something like a gas. And that means that it will result in a much higher temperature for that to occur, because you got to put more energy to do. Held together by very weak intermolecular forces have very low boiling points and melting points. That's why things that use weak intermolecular tend to be very volatile. They're able to go into the gas phase really easily because they're not being held together by a super strong force. Any questions on that there? So we're going to talk about here different types of intermolecular forces. So all these are intermolecular forces. The first type of intermolecular force is a dipole-dipole interaction. And dipole-dipole interaction, we saw that with polar molecules is where we get that. Polar molecules have a dipole moment, and that is represented by that arrow. Where it is more negative, where it's pointing, more positive. And what we're talking about here again is the molecule as a whole. The molecular polarity is polar. That means as a molecule overall, we have unequal sharing of electrons. We're not talking about bond polarity here. So we're taking like the molecular polarity, look at it like we did when we did bonding. Dipole-dipole interactions basically means you have two polar molecules, and because they have that dipole moment, they both will have pretty much a fixed positive side and a fixed negative side to their molecules, which means that when they interact, they have a really good way to interact with one another through the positive and negative side. And the thing of this is, because they are polar, no matter what you do to them, they will always have that positive side, negative side. They are good to go in terms of interacting. They don't have to rely upon, as we'll talk about some of these things, they don't have to rely upon something happening for them to get that positive, negative side. Just them and their way they share those electrons. They always have a positive, negative side, which means they're always good to go. When they do come together, they really do try to orient themselves in a way that maximizes the positive negative attraction, minimizes the positive sides being near each other, and the negative side and negative side being near each other. And no matter what you do, you're always going to kind of have that happen. You will have positive and negatives, positive and positives, and negatives being near each other, but they will keep kind of moving and rotating around as best as they can to sort of maximize that attractive force. As we talked about previously here, it's only about 1% as strong as covalent or ionic bonds. And that's because, again, those guys are intramolecular forces. So they're much weaker than that. Dipole is pretty much the way polar molecules interact with other polar molecules when they do not have the ability to hydrogen bond, and is really their major sort of force to do that. It is a relatively strong force as well. In addition, in terms of a dipole and polar molecules, there is another sort of interaction which is known as ion dipole. An ion dipole is pretty much what it sounds like. It is an ion attracted to a polar molecule. And this is essentially how we get ionic compounds to dissolve. So if we took something like sodium chloride, it would have a sodium ion and a chloride ion. And again, when it interacts with water, the negative side of water will be attracted to the positive ion, which is the oxygen in this case for water. The hydrogen part of water, which is the positive side, will be attracted to the negative ion. And this is how things really dissolve. It's a pretty good effective force, and it's still basically the positive negative attraction between those two guys. And that is why, again, ions and polar ionic compounds and water are soluble in each other, because they could use this ion dipole interaction to allow them to interact and really dissolve. Any questions on that? And that's obviously what happens when we do dissolve something. Those water molecules basically keep plucking off those ions, as there's a pretty good attractive force between them. So looking at dipole here.
Different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So again, this is a reminder that, it does tie together when you think about how molecules interact with each other. It does tie together with our Lewis structures and our molecular polarity. And again, if you have a polar molecule, it is most likely using dipole, especially if it does not have the ability to hydrogen bond. So let's talk a little bit about hydrogen bonding here. And as you can see in this example as well, they do try to maximize the opposites attraction and minimize those positive guys and negative guys being near each other. So what is hydrogen bonding? Hydrogen bonding really is a type of dipole interaction, but it is sort of classified by itself as a separate intermolecular force. It is essentially the strongest intermolecular force that you could have is hydrogen bonding, sort of the strongest, with dipole being really close. Hydrogen bonding is used by polar molecules that have the ability to hydrogen bond. So this is the main force for polar molecules interacting with itself and others that have the ability to hydrogen bond. So what is the ability to hydrogen bond means? It means that you have basically a hydrogen that is directly attached to a nitrogen, oxygen, or fluorine. So if you look at the periodic table, Nitrogen, oxygen, and fluorine are pretty much upper right of the periodic table, which means they are the negative elements you could have. With hydrogen, you get a pretty good separation of charge based on the difference in electron, and that creates a pretty good positive side and negative side that's happening in that particular case, and it allows it to hydrogen bond. So if you have something like water, which we were talking about, that is essentially how water interacts with things. Again, the oxygen being more negative, hydrogen being more positive, hydrogen directly attached to an oxygen, which means that that is hydrogen bonding. Things that can hydrogen bond tend to have pretty high boiling points and melting points because of that really strong intermolecular force. You typically would expect them to have a higher boiling or melting point than somebody else is using some other type of intermolecular force. This is also why things are, again, soluble in water, because when you have water and you have something else like our methanol, our methanol here does have this polar bond, which works really well with our polar bond in water. And again, they could hydrogen bond with each other, and that makes them really soluble in one another. So this is why certain molecules are soluble in water, because they have the ability to hydrogen bond. That's pretty much almost the right guess on any question asked. Why is it soluble in water? Because it has the ability basically to hydrogen bond with each other, and also why, again, it would have a much higher boiling point than something that cannot. A reminder that this is really an important part of being able to hydrogen bond. Just because something has hydrogens in it does not give it the ability to hydrogen bond. So although this, which is methane, has a bunch of hydrogens, it has no ability to hydrogen bond. None of those hydrogens are directly attached to a nitrogen, oxygen, or fluorine. In addition, that's a nonpolar molecule, and the carbon hydrogen bond is nonpolar as well. So there's really no separation of charge. There's no positive side or negative side, so it has no ability to hydrogen bond. So although, again, this guy is loaded with hydrogens, they are the wrong type of hydrogens, and they cannot hydrogen bond. If we take something like ammonia here, an ammonia hydrogen bond. Ammonia can hydrogen bond. It has a hydrogen that is directly attached to a nitrogen. It also is a polar molecule, so it does have that ability to hydrogen bond. So hydrogen bonding, which is really sort of a subset of dipole-dipole interaction, is sort of the strongest dipole-dipole interaction that you could have. Followed pretty closely to it is dipole-dipole interaction. So this is what I was saying earlier when we talked about dipole-dipole. That is for polar molecules that really do lack the ability to hydrogen bond. Like in that example there, our SO2 looks something like this. It is a, whoops, no dots there. It is polar and it does not have hydrogens. So it's going to use something like dispersion for, I'm sorry, something like dipole-dipole to interact because obviously it's polar, but it does not have that ability to hydrogen bond. Any questions on hydrogen bonding there?
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. Attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid state of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with 2 hydrogen atoms and 2 unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding.
So you can also see here, like we talked about, why ice has a lower density. They cannot get really tight to one another,
Structure.
as opposed to in liquid water like we see here.
Because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So again, in that earlier part of that animation there with ice, again, because of the strong hydrogen bonding, and when it comes into the solid state, those water molecules can't get really close to one another, which again gives water that sort of unusual property of being less dense than its liquid version. And that's because the volume of water increases in the solid state, which means density is mass over volume. So the density is actually less than what we see in liquid water. So again, here's our hydrogen bonding between different water molecules. The last type of interaction is dispersion forces, and dispersion forces, sometimes referred to as London dispersion forces. This is pretty much your nonpolar molecules, main route of sort of interacting with themselves and others. So dispersion forces are pretty much the weakest that you could have out of all those. And they are the weakest because they rely upon something happening to allow those molecules to get that sort of separation of charge. So if something is nonpolar, pretty much it is neutral, which means they need something to happen to allow it to gain a charge so they can interact with each other. So one way that it could happen is what is known as an induced dipole. So you could have an ion induced dipole, which means you have an ion near a nonpolar molecule. You could also have a dipole induced dipole, which means you have a polar molecule near a nonpolar molecule, which is essentially neutral. So the presence of these molecules or ions near a nonpolar molecule can have an effect on that nonpolar molecule. So if we take a look at this interaction here, because this polar molecule has a separation of charge, the electrons in this neutral guy is going to basically head away from the negative side. And what that's going to do is in this nonpolar molecule, which normally doesn't have a charge, because its electrons are now sort of distributed differently because of the presence of the polar molecule, it will now temporarily gain a charge. And now it temporarily has a way to basically interact with one another. This is why, for example, when we mix something that's polar, nonpolar, it kind of works a little bit for a short period of time, but over a long period of time, it's not able to maintain those interactions. You know, if you take something like oil and vinegar salad dressing, again, you can mix it and we'll mix for a short period of time, but as you leave it sit there, everybody separates out from each other. And that's because the nonpolar guy doesn't have a way to maintain that interaction. And that's different than what happens with our polar molecule. No matter what you do, that polar molecule has got a positive side and negative side. The nonpolar guy needs something there to cause it to get that charge. And that's why it's very weak. It will kind of go away and make a new interaction, go away, make a new interaction. And it's why you can't maintain that interaction for a long period of time. So this is one way that you can sort of induce a dipole and have dispersion forces. The other common way that nonpolar molecules and nonpolar molecules pretty much work is what is referred to as an instantaneous dipole. Sort of an instantaneous dipole happens when we have two nonpolar molecules. And because electrons are flying around in each of these molecules, it could happen that all the electrons, for example, end up over here, see on the right-hand side of this molecule. And what that's going to do is basically cause this guy on the left that normally would not have a charge will now gain a temporary charge. And again, if he's near the next guy next to him, the electrons in that nonpolar molecule will go away from the negative side. And now this second nonpolar molecule, which normally does not have a charge, will temporarily gain a charge. And now these two guys that did not have any type of charge has a way to interact with one another. And it's very temporary because those electrons could then flow back the other way and kind of break apart and make new interactions and so forth. This is what is sometimes referred to as polarizability. And that's the ability of those electrons to basically kind of move from one side or to the next in terms of their electron cloud. This is what is referred to as an instantaneous dipole, and it's essentially how nonpolar molecules basically interact with other nonpolar molecules. And that's why, again, it's weak, because it has to rely upon something happening to give them a charge to interact with. Any questions on that there? The strength of dispersion forces actually increases with molar mass. So if you're comparing two things that actually do use dispersion forces, the strength of the dispersion force increases with increasing molar mass. And that's because if you have an increase in molar mass, that means you probably have more atoms. If you have more atoms, that means you have more electrons, and you have a greater chance for these electrons to sort of shift around and move around. Also gives a lot more places for electrons to interact with. So if you ever have to compare, say, something like the boiling point of two nonpolar molecules where they both use dispersion forces, the one that is higher molar mass should have the higher boiling point, because, again, there's a greater opportunity for this polarizability to basically take place and a lot more places for interaction to occur. Any questions on that there? So here again is some dispersion forces.
Dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. The forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So as we were talking about earlier there, something like CH4, for example, although it does not have the ability to hydrogen bond, it is a nonpolar molecule, which means something like CH4, which is methane, would use pretty much dispersion forces as its main route of interaction. That is why a lot of organic molecules, as we might have talked about previously as well, are typically found as gases, because things like methane, propane, butane, they're all nonpolar, which means they're held together by these really weak sort of forces, and it doesn't take a lot for them to go into the gas phase. And under normal conditions, that's enough of conditions for them to be in the gas phase. That's also why if you continue to take organic at the end, they throw you in fume hoods when you work with organic molecules, because a lot of them are gases, and ones that are not gases can very easily go from the liquid phase into the gas phase pretty quickly, and can create some vapors, which can be hazardous, like those hexane and heptane stuff that we used in those experiments not too long ago. Those guys, as you might have noticed, when you open up the bottle, you could kind of smell some of it. And that's because, again, very quickly it could go into the gas phase, which is why, again, when you use those things a lot, they throw you into a fume hood. Any questions on intermolecular forces? So just to summarize one more time, the strongest is our hydrogen bonding, followed by dipole-dipole, which is pretty close. And our weakest out of all of them is our dispersion forces. And again, this is for nonpolar molecules. This is for polar molecules. No hydrogen bonding. And this is for polar molecules that can hydrogen bond. And again, they're really important, these intermolecular forces, as they really do account for a lot of the properties that we see in terms of how particular molecules interact with other molecules. Any questions on any of those there? Okay, so next thing we're going to talk about then is a little bit about vapor pressure, and a little bit how these guys sort of interact and why we get certain types of vapor pressure. So evaporation and condensation occur again at the same temperature, and that is essentially the normal boiling point of a substance. At the surface of any liquid, you have pretty much fast-moving liquid guys jumping out of the liquid phase into the gas phase. You also have slower-moving gas molecules that drop back into the liquid phase. So you have this sort of equilibrium happening in any situation. When we have this occurring, because we do have liquid water molecules or liquid molecules going into the gas phase, we end up with gas above the liquid. And when we have gases, we have pressure, and that is what the vapor pressure of a liquid is. It is basically the pressure associated with the gas form of that liquid that's sitting above the particular liquid. It's also why, for example, right, we have, you know, a little drop of whatever on the bench there, a little bit of water or something on the bench. It will evaporate relatively quickly because it will go through evaporation. And because there's air, the air will basically blow away those molecules and not allow them to come back into the liquid phase. Normally what would happen if the air wasn't there, they'd go in the liquid phase and some will drop back in, they'll go up and drop back in, but the air will push them away. And right, if you have a drop or something on the bench, it will eventually very quickly sort of evaporate. Now, if you take that same sort of water or whatever and you put it into a beaker, you're not going to get it to evaporate as quickly. You will still have those guys jumping out of solution and coming back into solution, but there's a lot of liquid molecules on the below the surface that need to work their way to the surface, so it will stay in that beaker a much longer period of time. So the pressure of the vapor in equilibrium with this liquid is known as the vapor pressure, and liquids that have a high vapor pressure are usually said to be volatile, which means they go into the gas phase really easily. That is, again, pretty much one of the only ways you could get a high pressure is to have a lot of gas molecules. So something with a high vapor pressure means there's a lot of gas molecules above the liquid. That means that they started in the liquid phase, so they're all jumping out of the liquid phase. And obviously, if you had something with a low vapor pressure, that means that you have a lot more of the guys staying in the liquid phase, a lot less of them coming out of the liquid phase into the gas phase. The vapor pressure is determined by the intermolecular forces. So if you have a really strong intermolecular force that holds together that molecules in that liquid, it's going to take a lot more energy for them to escape, and you will end up with less gas molecules above the liquid, and you would have a lower vapor pressure than something, again, much like methane or any of those organic guys is using dispersion forces. You would have a lot more vapor above the liquid. So something using dispersion forces should have a much higher vapor pressure because it's volatile and can go into the gas phase relatively easy. Something with using maybe hydrogen bonding would have a much lower vapor pressure in comparison because they're going to be held together a lot tighter. Less of them are going to be escaping the liquid into the gas phase. Any questions on that there? In addition, if we take some liquid and we put it into a flask and we put a stopper on it, if you take a look at the liquid level here to begin with, what's going to happen once you put that liquid into this flask with the stopper is pretty much it's all going to be evaporation is going to occur. So we're going to get a strong rate of evaporation happening, which is what we see here. As they evaporate, though, in this particular case, they got nowhere to go and there's no air going to blow it away, which means eventually these guys will turn around and start working its way back down into the liquid phase. And at some point, what's going to happen is we will get a rate of condensation going to occur in this case. And it will eventually reach equilibrium. And equilibrium, once again, does not mean equal, like the name might imply. What it actually means equal is talking about the rate. So the rate of evaporation will equal the rate of condensation in this case. So what that means is just as quick as somebody jumps out of solution, somebody will jump right back into solution. So essentially what that does is it doesn't necessarily mean you have the same amount out and into the solution. It means that as fast as one goes out, one will come back in. that will essentially lock everybody into place. So wherever it is at that point, it will lock how much liquid you have in place and how much gas you have in place, because they basically are just replacing one for one as they go back and forth. So there's not going to be a net change that's going to happen when those rates equal each other. And what you also notice, if you look at the liquid layer here, it will also end up being probably just a little bit less than what you had when you first put it in there, because when you first put it in there, there's no evaporation until you've got it in there. Then it was all evaporation, and then it hits equilibrium and locks everybody into place. Because now before, afterwards here, you do have some vapor molecules above the liquid and some vapor pressure. When you first put it in there, you really had no vapor pressure until we started to get some evaporation that occurred. Any questions on that there? All right, so to finish up this chapter here, talk a little bit about solids and some different types of solids. Good talk. Let's go back. So many solids or substances form crystalline solids, and there's a few different types of these type of solids. There's ionic solids, there's molecular solids, and there's a third type, which is sort of what happens with metals and covalently bonded to each other, these atoms, which is an atomic solid. So ionic solids like sodium chloride, they have a really very ordered pattern of how they come together. So when those ions come together in three-dimensional space, it is a very ordered sort of arrangement, and they have really long range order. As you'll talk about when you take 1A, you can actually just, for an ionic solid, just take a little piece, a little snippet, a little square of that three-dimensional structure of how they are put together. This is what is sometimes referred to as a unit cell, just like a little sort of portion of that big structure of how they are together. And from that one little square, you could essentially rebuild the entire structure of that solid. That's how ordered and repeatable the pattern is. You just need one little sampling of the pattern, and then basically just put them all back together, and you could rebuild the three-dimensional sort of structure. Molecular solids, like sucrose, using again some covalent bonding and interaction between them, like we have here with atomic solids. So this again is that very ordered arrangement of our negative ions and our positive ions, which are the smaller ones because they lost electrons. And again, that very repeatable pattern in an ionic solid. So let's take a look at each of these. Here we have diamond and our ionic solid. And another very common way that these guys sort of layer into each other is by sort of layers and patterns, like graphite, for example. Graphite is the same thing as a diamond. They're all very carbon. But what happens in graphite is you get more layers than what you can see there with our carbon and how the atoms come together here on the left. And here with water in its ice form, it gets sort of these nice layered patterns. And again, we can see our big open spaces there between the different water molecules in its solid form. So bonding in these guys, ionic solids are held together by really strong forces, the electrostatic attraction, and have very high melting points. And that is because, again, it is held together by intramolecular forces. So you might remember we talked about, I'm pretty sure, but you could take something that's an ionic solid, like in those really early experiments that you did, and you could heat the heck out of them. It'll never go into the gas phase. It will really just start to melt at some point, and that takes a lot of energy just to get it to start to melt. And again, that's because that intramolecular force is pretty much as strong as you could get to hold those things together. Molecular solids, on the other hand, are held together by intermolecular forces. Which again, as we talked about, are much weaker than our intramolecular forces. So because they're held together by those intermolecular forces, we tend to again see them start to melt at lower temperatures. We also can see them boil as well at lower temperatures because Something like water, you just need to get it up to 100 degrees to get it to start to boil and go into the gas phase. You could heat your ionic solid up to 100 degrees. It'll just start to melt, perhaps. It will, again, not go into a gas phase because of that really, really strong intramolecular force. Now, there's a couple of different ways that we can sometimes, for example, change metals. So when we have metals, we can do some type of alloying. And an alloy is really a mixture of elements that have metallic properties. And sometimes alloying is used to sort of protect metals. So for example, metals, when they go through corrosion, basically means that they get oxidized. They really go through a redox reaction. And one way that you could kind of protect metals is to alloy it with some other metals, and it will change some of the properties of that original metal and allow it to be a little bit more resistant to going through oxidation or corrosion. There's a substitutional alloy, which, like the name implies, you take out some of the atoms of the original metal and you basically put in atoms of another metal. So something like sterling silver is 93% silver and 7% copper. So some of the silver atoms are replaced with copper atoms. An interstitial alloy is basically when metals come together, there's these little holes between the different metals, and those little metals or holes between the metals are filled with a smaller sort of atom in there, like steel. So steel contains carbon atoms between different iron atoms. And again, it gives us some different sort of properties. So sometimes, like I said before, sort of doing an alloy or even galvanizing, for example, metals can change some of the properties of that metal. And a lot of times that's done in an effort to sort of protect it from going through significant amount of corrosion, which it would normally go through and go through a redox reaction. And here's our picture. So substitutional, we got some different atoms in there. And then here we have in these small little holes between the different atoms, we have another element there, like carbon, that's small enough to sort of fit there. Any questions on solids? We're not going to talk too much about it, but yeah. All right, that wraps up chapter 14. So we're going to go to chapter 11 here. Okay, so off to chapter 11 here. We finally got back to it. In this chapter, we're basically going to talk a lot about electrons and sort of relate modern atomic theory to what is happening with electrons. And a lot of what we'll look at in here, in addition to looking at electron configuration, which we sort of looked at when we're doing bonding, which is kind of where this chapter comes before. So we'll talk about how to write electron configuration, how electrons are in the atom. We're also going to look at the idea of what happens when electrons basically kind of jump from one energy level to the next and how they sort of come back down. So a reminder that when electrons go from, say, one energy level to the next, it requires a certain amount of energy to be absorbed, which is an endothermic process. And electrons has to go back down, say from a higher energy level to a lower energy level. That's going to require that energy to be given off in an exothermic type process. There is, again, the law of conservation of energy that we talked about, which means whatever amount of energy an electron, for example, gains in an atom, as it works its way back down, it needs to give off that atom the same amount of energy to the surroundings, as we don't lose nor create any type of energy different. So this is very similar to when you did like the flame test sort of experiment. When you stuck your sample into the flame, you obviously ignited it with a lot of energy. It excited all those electrons as they were working their way back down. You saw different colors in the flame that came off. And that's what we're going to talk about. As, for example, these electrons come back down, they will give off energy in the form of a wave. And that wave may correspond to colors. If it's in the visible part of the spectrum, may respond to or correspond to heat, if it's, say, in the infrared part of the spectrum. So a reminder that Rutherford's atom basically described the atom is having a small, dense positive core where we have protons and later found to have neutrons. Remember that most of the atom is empty space, and it's within that empty space of where the electrons are traveling. And as we'll talk more about in this chapter as well, and as we touched upon earlier, electrons do not travel in pretty circles. They travel pretty randomly about the atom. So we do have these electrons sort of traveling pretty random about the nucleus, which is positively charged there in the middle. There is, as we will talk about, some attraction obviously between the nucleus and the negatively charged electrons, as the nucleus is positively charged, and that gives some of these particles some of their properties that we think about. So let's talk about the first idea here of how energy sort of moves around from one place to the next. And a lot of experiments were done by a guy named Planck, and he did a lot of experiments with atoms. And basically at different temperatures, what he found was that atoms would sort of give off energy in what he defined as whole number multiples of energy. And this idea of energy being given off or absorbed in these certain definite amounts of energy is an important theme in quantum mechanics, which is known as a quanta of energy. And a quanta of energy basically means that in relationship to what we're going to talk about is the idea that as these electrons are transitioning from one energy level to the next, they will gain enough energy to go completely from one energy level to the next. And as they come back down, they will also lose a certain amount of energy that will allow them to go from one energy level to the next. So we had multiple energy levels and we had an electron, and if it gained energy, it would gain enough energy to get all the way, for example, all the way up there. And if that electron wanted to lose energy and stop right about there, it would lose enough energy to get all the way down there. It will never find itself like halfway between energy levels and go, I'm tired, I don't, just gonna take a rest here between different energy levels. So again, it will either sort of gain or lose energy in whole number multiples that allows them to completely transition from one energy level to the next. Sometimes people equate quanta energy to the idea of stairs. When we walk stairs, we usually have enough energy to get to this step, to this step, to this step. Again, we don't like go, I'll just stop like halfway up this step and just rest there because you're going to fall. And electrons, again, transition the same way. And the same idea as we come down steps. We usually have enough energy to come down one step to the next step to the next step. Again, we don't usually stop along the way. And that's sort of how electrons transition from energy levels to next. Just like people going upstairs, some people could do one step at a time. Maybe some people could do two steps at a time, maybe three steps. Probably not more than three steps, I mentioned. But you know, some people have enough energy to do multiple steps at a time. And it's the same idea with electrons. They have enough energy to either kind of go upwards in terms of energy level, multiple energy levels at a time, and come down as well. Obviously, as electrons go upwards in terms of energy levels, that's an endothermic process as the energy comes in. And as they are coming back down, that's an exothermic process. The energy is basically exiting. To understand basically Planck's idea, we have to talk about radiation. And really, this is how energy is really transformed or moves through space. And energy basically moves through space in the form of waves. So basically, waves come off as electrons again transition. So if we have an electron in a higher energy level, as it comes down, that amount of energy it had to lose has to be given off by the atom in the form of a wave of light, which could again correspond to the visible part of the spectrum where we see colors like red, orange, yellow, green, blue, indigo, violet, right? Roy G. Biv. Again, it doesn't necessarily mean that you always have to see colors. It could come off somewhere else in terms of its wavelength. And same idea as well. A wave of energy has to come in to allow those electrons basically to jump up to a higher energy level, again, similar to what you did when you put it into the flame. it gained all that energy, right? Those atoms as it went upwards. So let's talk a little bit about some properties of waves. Waves can be thought of as a vibrating disturbance, which energy can be transmitted. So there we have a wave going through the bird. And obviously, if you've ever been in the ocean and got hit by a wave, carries a pretty good punch sometimes, and it has a lot of energy associated with it. And again, that's how sort of energy moves through space when we do have these electrons sort of transitioning. Some more specific properties of waves, there are different parts to it. So let's talk about the different parts of it here. First off, the wavelength, which is lambda, is the distance between two peaks or troughs. So that is the wavelength. Wavelength is typically given in these three units, meters, centimeters, and nanometers. And I would say a lot of times meters and nanometers are very common units of wavelength. Nanometers pops up a lot because that is what visible light, like colors, are usually given, like red, orange, yellow, green, blue, indigo, and violet. A reminder that nano is 10 to the minus 9 is the conversion there. And again, that is a common sort of conversion is used. And also there's 100 centimeters in a meter. So the wavelength is the distance between peaks or troughs, which would be the guys on the bottom as well. The frequency, which is not V, but it's actually new, is the number of times that a wave passes through a particular point per second. The units of frequency are hertz, and a hertz is equal to a reciprocal second. So that relationship is important to know. A lot of times people will give you like the frequency in hertz, and people go, it's a hertz. So it is a reciprocal second. Reciprocal second is 1/seconds, right? Is the units that are associated with that. The amplitude is the distance from the midpoint there down. And the speed of the wave can be given by the wavelength times the frequency. And that usually a lot of times in meters per second. The wavelength is typically in meters. The frequency is typically in reciprocal seconds. So typically when we talk about how fast the wave is moving or how fast it is going through space, meters per second is typically the units that we associate with the speed of a wave. Any questions on that there? Light behaves like electromagnetic radiation, which again is that energy that's moving through space in the form of waves. When we talk about waves and we talk about particles like electrons, and we talk about sort of light, they're sometimes referred to as the dual nature of light. So a lot of sort of experiments have found the idea that particles like electrons can have wave-like functions, and waves can have particle-like functions. So we could a lot of times, as we'll do later on this chapter, apply sort of wave function to particles like electrons in terms of how they're moving, even though they're particles, because they can behave very much like waves in certain situations, and vice versa. Waves will have, very particle-like properties as well. We could think of like a stream of particles basically as sort of like a wave that's happening. Now, there's also a relationship when we talk about this energy that's coming off in the form of waves. We oftentimes refer to it as a photon of light. So again, as that electron comes back down, that wave that comes off is sometimes referred to as a photon of light. And again, if that photon has a wavelength that falls in that visible part of the spectrum, we will see colors. If it falls outside of that part of the spectrum, then we may see, not really see, but observe some type of other effect. There is a relationship between energy and wavelength. So if we have a really long wavelength, like a guy just kind of moving through space like this, we have a pretty long wavelength here. A longer wavelength will usually result in a lower frequency, and that usually results in lower energy. So something with a longer wavelength, you would expect to be a little lower in energy. And that's different than something with a smaller wavelength. So something with a smaller wavelength here. So something with a smaller wavelength here, 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 something with a usually we will have a much higher frequency, and that usually will result in higher energy. So something moving really quick with a repeating very quickly will usually be something that's much higher in energy than something that's just sort of taking its time and kind of cruising through space, which is a much longer wavelength. This also helps us understand when we see something like the different colors that come off. And when we talk about different colors, like the red, the orange, the yellow, the green, the blue, all those things, different colors have different energy associated with it just based on sort of the color that you see. And that's because they have different wavelengths associated with it as well. So when we see certain colors come off, you can make a pretty good guess as to maybe how many energy levels an electron transitioning based on sort of the colors that you see. Question on that there. So here is light as a form of a wave and also as a stream of packets of particles that have very similar sort of function. So here we see red, which has a much longer wavelength, which means this red is lower in energy than this blue color here, which has a much smaller wavelength, will have higher energy. So when we talk about colors, or Roy G. Biv, this side here, more purple, is usually higher in energy. This side here, red, is usually lower in energy. And that's again because red usually will have a longer wavelength. So again, if we see, you know, when we look at a transition that occurs, for example, as this electron comes off and you see a red light sort of appear or corresponds to a red light versus another one where maybe it's transitioning all the way down here and you see more of a purple or corresponds to more of a purple color coming off in terms of its wavelength. We can make a pretty good assumption that the red only had to go down one energy level, which means it's not going to give off a lot of energy. And that's going to be a much longer wavelength versus our guy that had to go down several different energy levels, which requires a lot more energy to be given off. And we're going to have a much shorter wavelength as you come through it. So other common features of electromagnetic radiation is the speed at which they travel. I personally go with 3 times 10 to the 8, but they would like you to learn this number, which I'm not quite sure how big of a difference it is, but it is 2.9979 times 10 to the 8 meters per second. That is the speed of light. That's about 186,000 miles per second. And c, which is our speed of light, is a constant. So you always have that number available to you. So when we deal with electromagnetic radiation and waves, this is the equation that we use. C is equal to the wavelength times the frequency. So that is our speed of light, which is our constant. This is our wavelength, usually in meters. And that is our frequency, which is 1/seconds, our reciprocal seconds, our hertz, right? Which is all the same. Speed of light is meters per second. So since this is in meters, once again, it's really important when you use this equation that you use meters for the wavelength. And again, sometimes it's a lot of times given to you in nanometers. So you do have to do that conversion. This is also a formula, which is C is equal to the wavelength times the frequency. If you want to solve for the wavelength, it would be C divided by the frequency. And if you wanted to solve for the frequency, it would be C divided by the wavelength. Good news is it's really the same calculation regardless of which one you are calculating for. You basically take the speed of light and divide it by either the frequency or the wavelength to get the other. That means if you just know one of those things, frequency or wavelength, you could calculate the other using this equation here. Again, here, unit-wise, you want to just be careful there of the wavelength. Any questions on that there? So once again, this is a number they expect you to know as you continue through your journeys here, I suppose. All right, so let's take a look at one here, see what you come up with. What is the frequency for a wave with a wavelength of 4.68 times 10 to the -7 meters? So see what you come up with here. Okay, so let's take a look here. So we can use our equation. C is equal to the wavelength times the frequency. Here we are looking for the frequency. We are given the wavelength, which is 4.68 times 10 to the minus 7 meters. We always have the speed of light, 2.9979 times 10 to the 8 meters per second. So in terms of the wavelength, we're good because, again, they are both in meters, so everything should cancel out. Okay. We're going to solve for the frequency by dividing the wavelength over. So the frequency would be C divided by the wavelength. Putting in our numbers, 2.9979 times 10 to the 8 meters per second divided by 4.68 times 10 to the minus 7 meters. Once again, the meters will cancel. You definitely want to make sure that you are using your exponent button like we've talked about many times. And we'll put that in. That's going to give us 6.41 times 10 to the 14. Once again, the units here are 1 over seconds, or if you want to go reciprocal seconds, or once again, that is a hertz, whichever unit you would like in that case. Any questions on that calculation there? All right, let's try another one here and see what you come up with. What is the wavelength in nanometers for a wave with a frequency of 5.6 times 10 to the 14 hertz? So in this case, we're looking for the wavelength in nanometers. Nano is 10 to the minus 9. And we're looking for the wavelength. We have a frequency given to us as 5.6 times 10 to the 14 hertz. Once again, that is the same as 5.6 times 10 to the 14 reciprocal seconds, as again, a hertz is the same as a reciprocal second. It's a 1-to-1 conversion. So once again, here, C is equal to our wavelength times our frequency. Here, we're going to be dividing our frequency to the other side. Wavelength is C divided by our frequency. We'll take our speed of light, which is 2.9979 times 10 to the 8 meters per second, divided by 5.6 times 10 to the 14 reciprocal seconds. In this case, the seconds are actually going to cancel. That will leave us units of meters. And that'll get us something like, we'll call it 5.4 times 10 to the minus 7 meters. We again wanted nanometers, so a reminder that 1 nanometer is equal to 10 to the minus 9 meters. So that is the proper way to use that conversion, not the other way around. That will get you 5.4 times 10 to the minus 7 meters. We'll go 10 to the minus 9 meters on the bottom as 1 nanometer. A reminder, that's basically 1 times 10 to the minus 9, if you need to put in your calculator that way. So divided by 10 to the minus 9 gets us something like 540 nanometers to sig figs based off of that number right about there. Yeah. Any questions on that particular one there? So again, you want to use this formula here if you got either the frequency or the wavelength given to you, and you're asked to calculate either one there. Any questions on that there? All right, one last thing here to finish this up. When these waves do come off as these electrons are transitioning, they will really correspond to somewhere on what is known as the electromagnetic spectrum. The electromagnetic spectrum basically are different areas and has different wavelengths, and this is a picture of electromagnetic radiation here and spectrum. And on this side of the spectrum, we have wavelength, and this is a longer wavelength, and means it has a lower energy on this side. On this side over here is a shorter wavelength and has a higher energy. So starting out over here on the right, we have things like radio waves, which has a longer wavelength, not as much energy. That is when you obviously dial into your car a certain radio station. you're doing the frequency, right? Like 95.5 megahertz, right? Is a frequency is what you're dialing in when you put your radio on in your car. If we go down, we next have something like microwaves. Microwaves have a little bit more energy, a smaller wavelength than radio waves, has enough energy to get water molecules moving really fast. So when you nuke your frozen pizza, it comes out in like 2 minutes, all cooked and happy. Coming down next is the smaller wavelength, which is the infrared part of the spectrum. That's usually where we feel heat sort of coming off. After the infrared, we get even smaller in terms of wavelength, and that's the visible part of the spectrum. That is where we see color. That is our Roy G. Biv. And as we talked about, even the colors here are separated in terms of energy. That has a longer wavelength red and a lower energy. Then over here, more violet, which has again a shorter wavelength and higher energy. I will say the visible part of spectrum, if the waves come off in that part, that again is where we see color, like fireworks, when they explode fireworks. And when they do the explosion, that's a lot of energy. All the elements within the fireworks, the electrons get excited. Depending on what elements are there, you see different colors. You go, ooh, wow, and all that kind of stuff. So colors in terms of the visible part of the spectrum are typically given in nanometers rather than meters in terms of units. So that is also why that nanometer to meter conversion is really important, because very commonly that is the units that you'll get for anything that is like red, orange, blue, green, and those type of colors. Next to it is ultraviolet part of the spectrum. That's why we put sunblock on when we go outside, right? So we do not get too toasty or anything like that. Has a lot of energy, can be damaging. Next to it, even smaller wavelength, we have X-rays, which is why they throw a lead vest on you and leave the room when they shoot the X-ray, right? Because it's a lot of energy happening. Why you don't take X-rays every single day and all that kind of stuff. And lastly, here we have gamma rays, which we talked about, I think, when we talked about the atom. That is basically just pure energy. It is a radioactive ray that has kind of no charge, is neutral, and it has a lot of energy given off. If you ever use anything that is a gamma emitter in terms of radioactive material, you just take a lot of precaution for that, because it does emit a lot of energy and you don't want to be near it. So again, smaller the wavelength, higher the energy, longer the wavelength, lower the energy. When those waves or photons of light or photon comes off, it doesn't necessarily always has to hit in here. It may hit outside those ranges, and depends really on the wavelength that you see happening as to where it will appear. You do need to know the electromagnetic spectrum, the order of everything, including the colors, which ones are higher in energy, lower in energy, longer wavelength, shorter wavelength, higher frequency, lower frequency. For me in here, you won't need to know exact numbers that break off. I can't promise you that as you continue your journey, but you don't need to know exact numbers that break off. But again, you need to be able to answer some type of question like that. Which one's higher in energy, longer wavelength, shorter wavelength? And again, the major categories, and then also the colors as well. Any questions on that? All right, we'll lay it up there.